People were seated indoors. The ceiling collapsed. 98 died in seconds. Washington, D.C., January 1922. Snow fell steadily for 3 consecutive days. Each storm deposited additional layers onto the previous accumulation. Temperatures remained below freezing throughout. The snow did not melt. It did not slide. It remained where it fell. The Knickerbocker Theatre stood at 18th Street and Columbia Road. Its roof was flat. Snow collected across the entire surface without interruption. There were no pitched sections to encourage shedding, no heated areas to initiate partial melting. The accumulation was uniform and static. By the evening of January 28th, approximately 2 feet of snow lay across the roof structure. The weight was distributed evenly. There was no visible deformation from street level, no sagging, no cracking sounds. The building appeared unchanged. Inside, the theater operated normally. The Saturday evening screening proceeded as scheduled. The lobby was lit. Ticket holders entered through the main doors. Ushers guided patrons to their seats. The auditorium filled to near capacity. Over 700 people sat in rows facing the screen. Snow continued to fall outside. The roof surface received additional weight with each passing hour. The load increased incrementally. There was no mechanism for removal. No intervention was planned. The snow simply remained, pressing downward with constant force. The structure bore this weight silently. No alarm was raised. No evacuation was considered. The audience remained seated as the film played. The Knickerbocker Theatre opened in 1917. Its design emphasized span and interior volume. The auditorium required an unobstructed sightline from every seat to the screen. This necessitated a roof structure with minimal internal support. The architectural solution was a flat roof supported by steel trusses. The trusses spanned the width of the auditorium without intermediate columns. This created the desired open space, but concentrated all structural load onto perimeter supports. The design was efficient for its intended purpose. It was not conservative in its margins. Building codes in 1917, Washington specified minimum load requirements. These calculations accounted for the dead load of the roof materials themselves and an estimated live load for snow accumulation. The live load assumption was based on typical winter conditions. Historical snowfall data informed these estimates. Extreme events were not the design basis. The roof structure met the code requirements at the time of construction. It was approved and certified. However, the safety factor, the ratio between actual capacity and expected load, was narrow. The design optimized material usage. Excess capacity was eliminated to reduce construction costs. The structure could support the anticipated loads but had little reserve strength. The trusses were constructed from steel members connected by riveted joints. Each joint represented a potential point of stress concentration. The connections were designed to transfer forces under normal loading conditions. They were not tested under sustained overload. The entire assembly functioned as a system. Failure of any single component would compromise the integrity of adjacent members. There was no redundancy. No alternative load path existed if one element failed. Snow weighs approximately 10 to 12 pounds per cubic foot when freshly fallen. As it compacts under its own weight, density increases. The 2 feet of snow on the Knickerbocker roof represented a distributed load significantly exceeding design assumptions. The total weight pressed uniformly across the entire roof surface. The steel trusses responded to this load by deforming slightly. This deformation was within the elastic range initially. The material strained but did not yield. However, as the load continued to increase with additional snowfall, certain members approached their yield strength. The stress was not evenly distributed across all components. Slight variations in material properties, joint stiffness, and load distribution created zones of higher stress. One truss or a specific region within a truss system reached its critical threshold first. The failure initiated at a connection point. A riveted joint began to separate. The load that had been carried by this joint transferred instantly to adjacent members. These members were already near their capacity. The sudden redistribution exceeded their strength. They failed in rapid succession. The collapse propagated through the truss network. Once a single truss failed completely, the load it had been supporting shifted to neighboring trusses. These were not designed to carry this additional load. They buckled under the increased stress. The failure cascade occurred in seconds. The entire roof structure lost its ability to support its own weight plus the snow load. From inside the auditorium, there was no advance warning. The ceiling materials concealed the structural members above. There was no visible sagging, no creaking sounds that penetrated to the occupied space. The lighting remained steady. The film projection continued. The audience sat unaware that the structure above them was failing. The roof fell inward. Steel trusses, wooden decking, plaster ceiling, and 2 feet of compacted snow dropped into the auditorium. The collapse occurred at 9:30 p.m. during the film screening. The audience had no time to react. There was no evacuation warning, no movement toward exits. People remained in their seats as the structure failed above them. The collapse was vertical. The roof materials fell directly downward onto the seating area. The balcony section received the greatest impact. The weight of the falling structure compressed the rows beneath. Seats were crushed. Bodies were trapped under layered debris. The materials created a compacted mass that filled much of the interior volume. The electrical system failed immediately. The auditorium went dark. The projection stopped. Dust and displaced air filled the space. Visibility dropped to near zero. The temperature inside began to equalize with the outdoor conditions. Snow that had been on the roof now lay mixed with structural debris throughout the interior. Survivors in less affected sections attempted to move toward exits. The normal egress routes were blocked or compromised. Some doors were obstructed by debris. Others were jammed by structural deformation. Movement through the darkened space was difficult. Those who reached the lobby or street level alerted emergency responders. The collapse had occurred without external warning. Passers-by outside were not initially aware of the failure. The trapped individuals were immobile. The weight of the debris prevented movement. Those conscious could hear sounds from other trapped victims but could not reach them. The cold air flowed freely through the broken structure. Body temperature began to drop among those who were injured or unable to move. The survival window was measured in minutes for some, hours for others, depending on the severity of their injuries and the degree of compression. Emergency response began within minutes of the collapse. Police, firefighters, and medical personnel arrived at the scene. The scale of the disaster became apparent as they entered the building. The auditorium was filled with structural debris mixed with snow and ice. The rescue effort required manual removal of materials. Workers used hand tools and bare hands to move debris. The unstable nature of the collapsed structure created ongoing risk. Shifting materials could cause secondary collapses. Rescuers worked carefully to avoid further injury to trapped victims. The process was slow. Each piece of debris had to be evaluated before removal to ensure it was not supporting weight above a trapped person. The outdoor temperature remained below freezing. Cold air circulated through the open structure. Victims who survived the initial impact faced hypothermia risk. Medical personnel treated injuries on site before attempting to move victims. Fractures, crush injuries, and internal trauma were common. Some individuals were conscious but unable to extricate themselves. Others were unconscious or deceased. The rescue operation continued through the night. Portable lighting was brought in to illuminate the work area. Additional personnel arrived to relieve exhausted workers. The debris field was extensive. Progress was measured in individual victims located and removed. Bodies were recovered from beneath layers of material. The final count took hours to determine as the entire structure had to be systematically searched. By morning, 98 deaths were confirmed. Over 130 individuals sustained injuries requiring hospitalization. The casualty count made it the deadliest disaster in Washington, D.C. history to that point. The building itself was a total loss. The collapsed structure remained in place as investigators documented the scene. The cause of failure was evident from the snow load and the collapsed roof configuration. The investigation focused on structural adequacy rather than operational factors. The investigation determined that the roof structure failed due to snow load exceeding design capacity. The steel trusses and their connections were found inadequate for the accumulated weight. The failure initiated at a single point and propagated through the system. No design defect or construction error was identified beyond the insufficient load capacity. Building codes in Washington, D.C. were revised in the following months. Snow load requirements were increased based on the January 1922 accumulation data. Design standards for flat-roofed public assembly structures were strengthened. Engineers recalculated capacity margins for existing buildings. Some structures underwent retrofitting to increase their load-bearing capacity. The changes extended beyond the district. Other jurisdictions reviewed their building codes. Snow load tables were updated to reflect more conservative assumptions. The concept of designing for extreme rather than typical conditions gained acceptance. The structural engineering profession incorporated the Knickerbocker failure into its knowledge base. The theater site was cleared. The debris was removed over several weeks. No reconstruction occurred at the location. The property eventually returned to other uses. The disaster itself faded from public memory relatively quickly. No permanent memorial was established. The event became primarily a case study in structural engineering rather than a remembered catastrophe. Snow accumulation on flat roofs is now treated as a critical design parameter. Building codes specify load values based on regional climate data and include safety factors for unusual weather events. Structural inspections check for snow accumulation during winter months. Removal protocols exist for buildings with inadequate capacity. The policy changes implemented after the Knickerbocker collapse persist without public awareness of their origin. The engineering response was institutional rather than commemorative.